Welcome to the Deep and the Better channel. Today we'll dive into one of the machine learning algorithms, the decision tree. We will go through the key concepts and then implement it from scratch in Python. Let's get started. A decision tree is a supervised machine learning algorithm that can be used for classification problems where we assign data to one of several classes, and for regression where we predict a continuous value. This means that to get a model to answer a question, we must first train it on a dataset where we already know the correct answer. The decision tree learns by dividing this dataset into subsets and further into smaller and smaller subsets, forming a hierarchical structure. The process continues until we get groups of similar elements where the answer to the posted question is either the same or very close. For this example, let's look at 2D plane with data points belonging to two categories. Each axis represents a feature of the data. I've intentionally chosen points that aren't linearly separable. However, we can see that points further from the center of the coordinate system tend to belong to the blue class, while those clustered near in the center belong to the red class. Additionally, the number of points in both categories is the same. Classifying a new point where the category is unknown involves a great deal of uncertainty about which class is correct. However, we can split the set of points into two groups based on a condition, hoping that the total uncertainty after the split will be reduced. By choosing a condition, we define threshold value on one of the axes. Any new point that met the condition is assigned to one of the subsets, and then we can assign it to the label that matches the training points in that subset. A subset that we no longer split because the labels of its points are uniform or similar is called a leaf. This terminates a branch of decision tree. Typically, one split is not enough. While the subsets become more uniform, they might not be homogeneous enough. Thus, they undergo further splits into smaller, more clearly defined groups. These multiple splits form a series of conditions in specific order. A new point for which we want to predict the label must pass through the series of tests until it's assigned a value associated with a specific leaf of the tree. A natural question arises. How do we determine the best conditions? Or in other words, how do we split the dataset so that it's not random? We want each split to be the best possible way to separate different types of data. This is where the concept of entropy and information gain comes into play. Let's introduce a concept of entropy, a term rooted in thermodynamics. Entropy measures uncertainty or disorder within a system, and it will help us quantify this for classification problem. Surely, we will break down the elements of the formula, but first let's understand what it means. If entropy is high, the uncertainty is high. In other words, if the point belongs to the group of points with high entropy, that information doesn't help much in determining its class. Conversely, if all points belong to the same class, we have complete certainty about the class of point and the entropy is minimal. Let's break down the formula. P is the probability of occurrence for a point in given category X with index I. In other words, it is the ratio of points in category X to the total number of points. The probability is multiplied by logarithm of the probability with a base of 2. Notice that by definition, probability is less than or equal to 1. The logarithm of such value is always negative, which is why a minus sign is added in front of the entire formula. Finally, These values are summed across all categories indexed by I. Here's what entropy looks like for 6 points belonging to one of two classes. Maximum uncertainty has a value of 1 when the data is evenly distributed between the two classes. Minimum uncertainty occurs when all elements belong to one category, where the entropy value is 0. Our goal is to create a subset with minimum uncertainty, meaning high certainty about the classes of their elements. When splitting data into subsets, we want the total entropy after the split to be smaller than before. The total entropy of the system after the split is calculated as a weighted average of the entropies of the resulting subsets. What we want to observe when splitting the dataset into two subsets is information gain, essentially a reduction in uncertainty. We calculate this as a difference between entropy before and after the split. Among all possible ways of splitting the dataset, we should choose the one with the highest information gain. To calculate information gain, we use entropy for classification problems. For regression, we need to use a different function, such as variance, which measures the deviation of points from the mean value. In regression, we aim to minimize the diversity of predicted value in the subset after the split. The table presents alternative function for each type of problem. Now let's move to the code editor. First, we need to import the necessary libraries. We will use counter to analyze frequency of classes in our data and NumPy for numerical computations like calculating entropy and information gain. The entropy function calculates the uncertainty in our data. We compute a histogram of values in the labels y and then calculate the probabilities for each value to get the entropy. Next, we start implementing the information gain function, which will measure how much the uncertainty decreases after splitting the dataset. The first step is to calculate the entropy of entire dataset, the parent. We then add a split into left and right part based on the threshold, split thresh. We check which points satisfy the condition and assign them to the appropriate subset. If one of the subset is empty, meaning all the points belong to one subset, the information gain is 0, and no split can reduce the dataset's entropy. Now we calculate the entropy of the subset. We weight this value by the number of points in each subset and calculate the information gain as a difference between parent's entropy and the weighted average of the subset entropies. In the decision tree classifier class, we define the parameters of our decision tree, such as the minimum depth and minimum number of samples required to make the split. The best split function searches through all possible splits for each feature. The goal is to find the split with the highest information gain. We add a loop that iterates through all possible threshold values for each feature, calculating the information gain and returning the best split, defining by the feature index and the split threshold. The grow tree method handles the recursive building of the decision tree. We first check the stopping criteria, whether the maximum depth is reached, the dataset is homogeneous, or the sample size is too small. We then add a tree building process. We find the best split and create subtrees for both left and right sides. The process is recursive until the stopping criteria are met. The split function divides the dataset based on the selected threshold. It returns the indices of the elements in both left and right subsets. The most common label function returns the most frequent label in dataset, used for assigning the label of the leaf node. The traverse tree method walks through all decision tree, checking which branch the sample falls into until it reached a leaf. Finally, the fit function starts the building tree process using the growth tree method. And predict function predicts the classes of the test data by walking through the decision tree for each sample. Now we can prepare the data for training and testing our classifier. We import the built-in model from scikit-learn, the function to split the dataset, and the iris dataset. We load the iris flower data, which will be used to train and test the model. Now, let's import our classifier. We train our model and calculate its accuracy on the test set for our implementation. For comparison, we train and test the decision tree model using the built-in implementation from scikit-learn. The regression model in our decision tree looks very similar. We only need a few modifications, but the general principle remains the same. I won't go through every line of code, but I will highlight the main differences between the classifier and regressor. Of course, both code files are available on my GitHub. The first difference is that instead of using entropy function, we calculate the variance using the variance function, which directly leverages a built-in function from the NumPy library. Instead of information gain, we have the variance reduction function, which inner working are analogous to its counterpart in the classifier model. Its purpose is to measure how much the variance of the dataset decreases after the split. When building the tree in the grow tree function, instead of filling the leaf node with the most frequent class, we assign the average value of the element in that subset. For regressor, we also added additional exit conditions due to the nature of continuous numerical labels. These conditions serve to terminate the tree branch construction if there is no way to further split the dataset that would yield an information gain. Finally, we can run a regressor model and compare it with the result of built-in model from scikit-learn library. We will use California housing dataset from scikit-learn, where predict housing prices in California. And that's it for today. In this episode, we took a closer look at the decision tree algorithm, both from theoretical and practical perspective. I hope I managed to explain how the algorithm works clearly and that you now feel more confident about applying it in your own projects. You can find the code for both models on GitHub. The link is in the description below. Thank you for watching and see you in the next episodes.